Yes.
Yes.
Okay, thank you. So thank you everyone for being here for my talk. So I will show you in my talk my research program probing exotic structure using one nuclear transfer reactions. So this is the outline for my talk. At the beginning, I will show you some general questions for nuclear physics. And using one nuclear transfer reactions, we can answer those questions. For example, we can enhance our understanding of exotic structures. For example, in beryllium 11 and beryllium 12. We can also measure the resonances in weak bonding nuclei and test the role of coupling to continuum. So having this physics motivation, I will show you some instrumentations for transfer reactions. Transfer reaction is also a very powerful experimental tool to study the nuclear effective interaction. So there are a lot of opportunities with FRIB beam coupling to AT-TPC and SOLARIS. I will show you some of these future plans. So major questions raised by the whole physics community has been stressed in the long-range plan for nuclear physics. Like this question includes many aspects. For example, where do the nuclei and elements come from? What combination of neutrons and protons can form a bound nucleus? So the answer to this question require better understanding in both experiments and theories. So the new experiment should integrate with knowledge from theories, astrophysics, and computational science. So understanding the nuclear structure and nuclear force, which drive the underlying changes in the orbital spacing, is topic of high priority in the current nuclear structure research. So this has been highlighted in a few broad scope documents and has led to the construction of the next generation rare isotope facility. So accessibility of rare isotope beam allows us to answer those questions raised above. So in this talk, I will show you using one nuclear transfer reactions, we can answer those questions in the following aspects. We can enhance our understanding of weak bonding nuclei by the direct reaction measurement. We can determine the shell structure and test the configuration interaction series. We can measure the resonance in weak bonding nuclei and test the role of coupling to continuum. So as I show you here, throughout the chart of nuclei, the changes of shell closure has been observed. For example, in the very light nuclear region, the N equals 8 disappearance has been well studied in beryllium and lithium. In oxygen, there are two new magic numbers, N equals 14 and N equals 16. So in the heavier system, there are two islands of inversion around N equals 20 and N equals 28. And also include the possible new magic number N equals 34. So there are many factors that can contribute to the change of shell closure. For example, the weak bonding effect, the change in the spin orbital interaction, and the tensor force. So it's very important to track the changes of the single particle excitations in order to map out the mechanism driven behind. So transfer reaction provide a very important experimental tool to study the shell evolution and the effective interactions. The angular distribution determines the angular momentum of the transferred nucleon. The single particle energy can be determined by the weighted average of the spectroscopy factors. So the spectroscopy factors can be determined by comparing the experimental angular distribution to the DWBA calculation. So so the different single particle excitations can be therefore isolated. So we can track these single particle excitations as a function of neutron and proton numbers. So this will help us to understand the mechanism behind this evolution. So in addition, it is well known that the single nuclear adding reaction provide the vacancies, while the single nuclear removal reaction provide probe the occupancies of the orbital. So using this principle, you can see that the nickel isotope occupancy and vacancies can be determined. So based on this principle, the quenching factors for one nuclear transfer reactions has been determined to be around 0.4 to 0.7 using consistent optical model parameters. So if we can measure most of the single particle strengths in one experiment, we can normalize these spectroscopy factors using the sum rule. And in this case, we can reduce the uncertainty from the absolute cross sections or optical model potentials. So that's why we prefer to use the relative spectroscopy factors rather than the absolute values. So the one nuclear transfer reactions can be carried out using normal or inverse kinematics. Usually normal kinematic experiments were carried out using spectrometers, so the resolution can be as good as 10 keV. So the inverse kinematics study opened the possibility for studies on the rare isotopes, but the resolution can be limited by the beam quality and the kinematics compression. So here I show you some of the work, some of the very famous equipment all around the world, which has been designed to carry out the direct reaction in inverse kinematics. So most of them use the silicon detector to detect the light charged particles emitted from the target, and some of them use the germanium detector coupling with the silicon detector to improve the resolution of the study. And another well-known equipment, Helios, has overcome the kinematics compression by using the magnetic field. So this equipment will be used in some of the work I will present to you later. So for example, here for the DP reaction, we usually use the silicon array upstream of the target. So the protons were detected by the silicon array, and the heavy recoils go into forward angle and detected by the annular silicon detector near the forward angle. So you can see that the projection of the inverse spectrum can give the excitation energy spectrum. In this case, we get this excitation energy spectrum of fluorine 22, and we can determine the angular distribution for each state. And by comparing to the DWBA calculation, we can determine this L equals 0 and L equals 2 spectroscopy factors for each state. So as I stated above, we can determine the single particle energy of the SD shell orbital using the weighted average of the spectroscopy factors in this case. So we can even determine, we can even compare to the shell model calculation using different interaction to test these different interactions. We can see that the USD interaction underestimate the D3½ single particle energy by 0.5 MeV. So we can even determine the matrix element in the D5½ orbital using these different nuclei. So I won't go into detail later in this part. I will show you some of the examples in the final part of my talk. So having transfer reaction as a very powerful tool to study the structure of nuclei. So if we look into the chart of nuclei in the light region, there exist many examples with exotic structure like halo nucleus. So the 2-neutron halo nuclei has very pronounced 3-body structure. For example, helium-6 and lithium-11. So some of the nuclei, although they do not have a halo, but they still show very pronounced 3-body structure with 2 valence nuclei coupled to the core. For example, beryllium-12, beryllium-14, and oxygen-26. So some nuclei, the ground state is a resonance with the neighboring nuclei being the boron system. So here I show you an important region around the beryllium and the lithium for n equals 8 and n equals 7. So you can see all these different exotic structure in this region. So in this light region, the structure of beryllium isotopes provide a great testing ground for many different nuclear models. For example, the small number of valence nucleons allows the in-depth study of the single particle structure in shell model, as well as the ab initio approach. The deformation degree of freedom allows the test within cluster model and the Nielsen model. So you can see how the structure of this nuclei varies with each other within this isotopic chain. You can find the cluster structure, halo structure, three-body system, and the breakdown of n equals 8 magic numbers here. So starting from beryllium-11, which is well known as the one-neutron halo nuclei. So the ground state is 1/2 plus. Its configuration is dominated by one neutron in s1/2 orbital coupling to beryllium-10 core. Its first excited state is 1/2 minus. So the level order of the ground state and first excited state are inverted compared to the conventional shell model level order. So this indicates the breakdown of n equals 8 magic number in beryllium-11. So its neighboring isotone, boron-12, the ground state is dominated by the configuration within the P shell. So there is very little intruder configuration in the ground state of boron-12. If we remove one proton from P3/2 orbital, we will be able to strongly populate states in beryllium-11, which has a dominant configuration within the P shell. But the negative parity states with two particles excited to the SD shell orbital will not be strongly populated, although they may allowed by the transferred angular momentum. So this experiment was also carried out using Helios, but with the silicon ray downstream of the target. So you can see we can strongly populate the first excited state of beryllium-11, and due to the magnetic field, so this states shows as a straight line in the inverse state spectrum here. So by getting on the different states populated here, we can get the angular distributions for each state. By comparing to the DWBA calculation, we can get the spectroscopy factors for each state, and we can compare our result with the shell model, Nielsen model, and the ab initio approach. So compared to the shell model, we can see that the shell model can predict the spectroscopy factors, but the level order of the second 3/2 minus and the first 5/2 minus states are inverted compared to the experimental level order. So the VMC model ties the prediction for many body systems to our understanding of nuclear interactions. So it gave a corrected level order. So the Nielsen model underestimates these two spectroscopy factors for the higher excited state, indicating boron-12 is not a strongly coupling picture. The calculation within the decoupling picture is under investigation, but it shows a much better agreement with the experimental result. So looking at beryllium-11, the immediately question goes into beryllium-12, which has one more neutron outside the beryllium-10 core. So the beryllium-12 has 4 particle bond state. the lower energy of the 3 excited state indicates the breakdown of n equals 8 magic number. It also has an isomeric state with a lifetime of around 300 nanoseconds, which measure the decay via emission of electron pairs. So due to the breakdown of n equals 8 magic number, we can expect there can be strong mixing in those two 0 plus state in beryllium-12. So using the configuration mixing theory, we can write down their wave functions in the following format. I show you here, with the last 2 neutrons occupy the S1 half, D5 half, or P1 half orbital. So summing the experimental and the theoretical result, we can see that the different experiment and the different theories give very different predictions for these individual intensities within these 2 0 plus states. So we carry out the beryllium-11 DP reaction at RSMP Osaka University to selectively populate the ice wave intensities within this 2 0 plus state. So the beryllium-11 in pump on the CD2 target, the protons were detected by the annular silicon detectors at the backward angle, and the beryllium isotopes goes into the forward angle detected and stopped in the 0-degree telescope. So in order to isolate the second 0 plus state from other excited state, we use the scintillator detector to surround the 0-degree telescope and detect the 511 keV gamma ray emitted from the implanted beryllium-12 here. So from the PID on the 0-degree telescope, we can see that we can isolate these different beryllium isotopes. By getting on beryllium-12, we can get the excitation energy spectrum of beryllium-12, and we can get the angular distribution for the ground state. And by comparing to the ADWA calculation, we can get the spectroscopy factors for the ground state. So for the second 0 plus state, we use the triple coincidence of beryllium-12 in the 0-degree telescope and the proton at the backward angle and the 511 keV gamma ray in the scintillator detectors. So now we get the spectroscopy factors for these 2 0 plus states. So we use the ratio of these two spectroscopy factors to represent the ratio of the ice wave intensity within these 2 0 plus states. So we use the ratio instead of the absolute value because we don't need to worry about the absolute cross-section, and we reduce the uncertainty from the optical model potential, and we don't need to worry about the crunching factor here. So together with the orthogonal and the normalization relationship in the configuration mixing theory, we can get the individual intensity for the S and D orbital within this 2 0 plus state. So this is our experimental result. We can see that from our result, the ground state of beryllium-12 is dominated by the configuration within the D orbital, but the isomeric state were dominated by the normal configuration within the P1 half orbital. So we compare our result with the shell model calculation. We can see that the shell model calculation underestimate these two dominant configuration in these two states. So we lower the D5 half single particle energy by 0.5 MeV, and we find a much better agreement with the experimental result. So our results show that beryllium-12 ground state is dominated by the D5 half intruder configuration. This is a dramatic change compared to beryllium 11, where the ground state is dominated by the ice wave intruder configuration. So this is possibly due to the stronger pairing in the d5½ orbital, which make the pair of neutrons tend to occupy the d orbital. And another possible reason is that the deformation degree of freedom lowers the d5½ orbital energy, as can be seen in the Nielsen diagram. So we can see that the level order can also be corrected for the second 0+ state and the 2+ state if we lower the single particle energy of the d5½ orbital. So, but we can still see that the excited state of the 1- state are still overestimated in all these shell model calculations. So this indicates there are still something missing in the shell model calculation. So possibly because we didn't consider the coupling to continuum effect here. So in the next part, I will show you our result about beryllium-12 resonances and how we can compare to the theoretical calculation and see the coupling to continuum effect here. So considering the breakdown of n=8 magic number, we can expect in the low-lying state of beryllium-12, there can be some one particle, one hole configurations across n=8. So if there is one neutron in s1½ orbital and another neutron in p1½ orbital, they can couple into 1- and 0- states. So the wave function of these two neutrons can be found at a larger radius than other high L value orbital. So we can expect these states can strongly couple to the continuum. So from the systematic of the single particle energy of L=0 and L=1, we can see some reduction of this energy across the particle emission threshold. So we expect the excitation energy of the 1- and the 0- to be reduced in beryllium-12. So the 1- state has been found at 2.7 MeV, but the 0- state has not been found below the neutron's emission threshold. But we can expect the 0- state to exist somewhere just above the 1 neutron separation energy, which will decay via emission of L=1 neutron. So, but if the excitation energy state of this 0- state is even higher, it will decay via emission of L=0 neutron. So this will make the size of the state very large, make it a virtual state, which is not easily detected experimentally. So somewhere just above the 1 neutron separation energy provides a convenient location for the 0- state. So it can even align with the neutron emission threshold and enhance its one particle, one hole configuration. So looking at the PID on the 0° telescope, we can see some beryllium-11 and beryllium-10, which may result from the unbound state decay of beryllium-12. So we expect this unnatural parity states, 0- state, to be strongly populated in the one-nucleon transfer reactions due to its one particle, one hole configurations. So gated on beryllium-11, we can see that there are at least 2 states that were strongly populated here. So with one state just above the 1 neutron separation energy, the other state above the 2 neutron separation energy, but has a very large 1 neutron decay branching ratio here. So we can get the angular distribution and comparing to the DWBA calculation using the Vincent Fulton technology, both states agree with L equals 1 neutron transfer. So this limited the spin parity possibility, and both states has a dominant decay branching ratio to beryllium-11. So in order to include the three-body structure and the continuum coupling effect in beryllium-12, we adopted the three-body calculation using the Gamow couple channel approach, which uses beryllium-10 as a deformed core with the Saxon universal potential to describe the coupling of the two valence neutrons to the core. So the detailed for these interactions can be found in this paper. It has been used to describe oxygen 11, oxygen 12, and nitrogen 11. So compared to the shell model calculation, we can see that in the Gamow couple channel and the Gamow shell model calculation, the excitation energy of the weak bonding states or unbound states were reduced in these two cases. So, and the Gamow couple channel approach gave a very close prediction for these two states observed experimentally. So the reduction of the excitation energy in these two cases is possibly due to the following reasons. Because in the shell model, we use the harmonic basis, so the nuclei behave like a closed quantum system. While in the Gamow couple channel or Gamow shell model calculation, we use a more realistic interaction with the diffused edge to represent the interaction between the valence nuclei and the core. So the nuclei behave like an open quantum system. The coupling to continuum effect can be taken into account self-consistently here. So we can also look into the interplay between the single particle and structure and the two neutron correlation using the Gamow couple channel approach. So we can even compare the result of beryllium-12 to its isotone lithium-11, which is even more weakly bonding. So we can see that the ground state of both nuclei, including the second 0+ state in beryllium-12, show a mixture of dineutron structure and the Sig-like configuration. So for the second 0+ state, we can see it's more likely to have a halo structure similarly to the ground state of lithium-11. For this 1- and 0- states, because they have dominate one particle, one hole configuration. So the two valence neutrons are less correlated. So the two neutrons tend to form a more uniform distribution here. So we can even find a similar state in lithium-11, which is the 3½ and 5½ state. So the excitation energy of these two states predicted by this Gamow couple channel approach agree quite well with the experimentally observed soft dipole resonance in lithium-11. So as I show you here, there is a linear systematic behavior for this one particle, one hole state in this n equals isotone. So you can see the sensitivity to continuum for this lithium-11 and the beryllium-12 one particle, one hole states. So having all this physics motivation, I will show you some instrumentations for transfer reactions. So the existing and future facility at FRIB and Atlas provide increasing opportunities for the study on the rare isotopes with direct reactions. So with the energy upgrade of Rare Isotope Beam, we can get beam energy to 6 to 12 MeV per nucleus. So direct reactions like transfer elastic or inelastic scatterings can immediately take advantage of these unique beams. So the active target and projection chamber and the SOLARIS coupling to this beamline will greatly expand the possible range of reaction study one can do. So SOLARIS can handle both AT-TPC and the silicon array mode. So in the silicon array mode, it's similar to Helios, but with the solenoid a little longer than the solenoid in Helios. So it allows both silicon array upstream and the downstream. So we can, in this setting, we can measure the reactions with both backward and forward angle. So it allows a different reaction channel to be started in the same environment. So in this silicon array mode, it's ideal facility to carry out the direct reaction with beam of around 10 to the 4 to or even more. So the SOLARIS can also handle the AT-TPC mode. So the AT-TPC is a large volume gas field detector. The nuclei in the gas molecule act as the target isotope as well as the tracking media. So it has a very large effective luminosity, which allows direct reactions to be carried out as low as 100 particles per second. So it can get more advantageous when operating with the magnetic field, where longer trajectories can be recorded within the active volume of the AT-TPC. So it also opens a possible way of proton adding reaction, which allows the study for the rare isotope on the proton-rich side. So there has been some resonance scattering measurement with the AT-TPC, but the transfer reactions is still under investigation, which will be carried out during the transition period from NICL to FRIB. So the reaccelerated beam in FRIB coupling to SOLARIS in silicon array or AT-TPC make it possible to obtain very detailed information for the key nuclei. For example, we can study the mechanism behind the experience of N equals 8 in magnesium. We can study the interplay between the PSD shell orbitals in carbon isotope. We can study the how the changes of N equals 14 and N equals 16 in this region. So in the heavier system, we can study N equals 28 changes in the isotopes around the sulfur region, and we can study the mechanism behind the appearance of N equals 34 in calcium. And in the heavier system, in nickel, we can even study the PF shell single particle structures about N equals 40 and N equals 50. So with transfer reactions, we can also study the nuclear effective interactions. So this was inspired by the Schaefer-2 method in this paper. So we can deduce the effective interaction and the two-body matrix element using the nuclei with 1 or 2 nuclei away from the closed shell. So deducing the effective interaction from experimental data is the key to understanding the shell evolution and to improve the shell model calculation. We can use this effective interaction, our matrix element, and apply it into the configuration interaction calculation to get the refined spectrum. So we can see that using this principle, the all nuclei provide great opportunities for study the diagonal two-body matrix elements. So the odd proton and all nucleon can couple with each other and result in many different multiplets with different G values. The single particle component in these multiplets can mix with each other. So the transfer reactions can be used to isolate these different single particle strands. So we can get the two-body matrix element here. The average of these multiplets determine the multiple interaction, which drive the underlying changes of the orbital spacing. So this kind of study can be expanded in more weak bonding system. For example, in this around this closed shell nuclei, and we can study if there is a reduction in the effective interaction over the two-body matrix element away from the stability. And most of the beam should be available with FRIB, and some of the beam should be already available with RISA or Caribou at Atlas. So having shown you some of the research plan within the next few years, I will also show you some research plan within next year. So within the very near future. So we want to commission the AT-TPC and the SOLARIS using the long-lived beam during the transition period from NICL to FRIB. So there has been hot debate about if there is a reduction in the sudden reduction in the spin orbital splitting in silicon-34, and if this can be linked to the presence of the proton bubble in silicon. And but the weak bonding effect seems to show a smooth trend for the spin orbital splitting, as I show you here. So we want to study the spin orbital splitting in the N=19 isotone. We want to study the silicon-32 reaction to get the systematic of this spin orbital splitting to see if there is a sudden change in the spin orbital splitting in silicon-33, and to see if this can be linked to the possible bubble effect here. So due to the weak bonding effect, as calculated here using the Woods-Saxon potential, we can see a smooth change of the spin orbital splitting in this isotonic chain. And but the excitation energy of the 1/2 minor state in silicon-33 are playing a crucial role in determining this trend. So this state will be able to strongly populated in silicon-32 DP reaction according to the shell model calculation. So this experiment will be carried out during the transition period from NICL to FRIB. So we also want to commission the AT-TPC using transfer reaction. So we want to test the capability and the resolution for the AT-TPC for transfer reactions. So we also want to confirm the parity of the 3.4 MeV state in beryllium 11, and we even can compare our experimental result with the latest reaction calculation to unify the structure and the reaction. So in the simulation, you can see that the different reaction channel like DD, DT, and DP can be populated in the active volume of the AT-TPC. So there are some other facilities around the world. For example, the Isuda beam provide great opportunities for carrying out the DP reaction at the desired energy. So we have some plan to carry out this beryllium-11 DP reaction to isolate the second 0 class state from the 2 class state directly, and we can take advantage of the good resolution of ISS, which is similar to Helios and Solaris. So with the RCMP beam of around 20 to 30 MeV per nuclear, it provides ideal possibility for starting the D helium-3 alpha T alpha D reactions. So there are many opportunities with RCMP beam, as I show you possibly in some of these regions. So we also have some plan to propose some experiment in the next RCMP pack. So here I come to the summary of this talk. So at the beginning, I show you some overarching questions for nuclear physics. So this includes the nature of nuclear force and the origin of the symbol pattern in the shell in the shell structure. And using the one nuclear transfer reaction, we will be able to answer those questions. For example, we can get the new experimental insight in this nuclear to get the theoretical development. For example, in here, I show you some work for the beryllium-11 negative parity state. We test these different theoretical predictions for these states. And we can enhance our understanding of the nature of weak bonding nuclei by the direct reaction measurement. For example, in this work, in this talk, I show you, we study the configuration mixing of the 0 plus state in beryllium-12. So we can even measure the resonance in weak bonding nuclei and compare to the different theory to test the role of coupling to continuum. For example, we found that the coupling to continuum effect is essential to describe the structure of beryllium-12. So we can even study the effective nuclear interactions using transfer reactions. We can determine the shell structure and test the configuration interaction theory. So we can even probe the nuclear force in the very weak bonding system, which can be realized during the future beam at FRIB. So with all this physics motivation, there are a lot of possibility in the future. In the future with the reaccelerated beam at FRIB, and we can couple those rare beams with AT-TPC or SOLARIS, which so I show you at the end of the talk that there are a lot of opportunities. We can study the spectroscopic information on this key nuclei around these isotopes. So I also show you some of the research plan within the very near future. We want to commission during the transition period from NICL to FRIB. So with this slide, I want to thank all the collaborators which has been contributing to the work I show you in this talk. So any questions and comments are very welcome here. Thank you very much for your attention.
Actually, thank you, Jie. Very nice presentation. Please go ahead. If there are any questions or comments, just raise your hand or just go ahead and ask. Let me see. I don't, maybe I'll ask you a question, G. In your discussion of fluorine 22, a la Schiffer-True,
Yeah.
I wonder, of course, it's a relevant measurement and one needs to do that, but it seems like some of these light nuclei, like give me the example of oxygen 24, recently explored by the Japanese colleagues. It seems that you add a proton to it in fluorine, and the core changes dramatically from something that would be a closed shell nucleus to something polarized. So this question of getting the effective NN interaction needs to be taken with a grain of salt, because if you polarize the core very strongly, then I'm not so sure that that's true, but more like a comment.
Yeah. So if we, in fact, if we want to use this Schiffer-True method to study the matrix element in using this different nuclei, but we need to make sure we are using a closed shell. So for example, here we use oxygen 16, oxygen 22, and silicon 28 as a core. So in fact, we can see there is a different from if we get the matrix element by assuming silicon 38 as a 28 as a core. So that means this core might be not so good.
Yeah, in other words, I think it's not that the method will not be valuable, it's just that the strength could be well fragmented, and then your analysis relies on centroids and all that, and you may miss some of them.
Yeah, you need very good statistics in order to get those fragmented single particle strengths.
Thank you. Any more questions for G or comments? Well, it seems like you convince us very well. There is no many questions as I see. Okay, well, in that case, let me thank you again on behalf of the committee and the participants, and wish you all the best. No, there is a question. Oh, is that a question mark, or is
that's just applause. Sorry.
Yeah, of course. Thank you, Mark. I thought you were going to talk about beryllium. So yeah, thank you again for a very nice talk, and we wish you all the best. And we'll see you all again on November 12th. So stay healthy and keep well.
Thank you.
So G,
Hi.
maybe we can chat briefly.
Yeah.
So I will stop now the video. I will, sorry, I will stop the recording.